New monitoring tools are helping utilities detect rare contamination events amid multiple complex data signals, leading to better water quality and security.
Some of the first water infrastructure security work, the risk assessment methodology for water, was started at Sandia and has been adopted across the country now. And this is kind of the follow-on piece to that.
Water distribution networks were designed and built to serve customers and provide firefighting capabilities. They were never intended to be secure systems. But in 2003, a Homeland Security presidential directive laid out a challenge that critical infrastructure must be better monitored. Sandia National Laboratories is partnering with the U.S. Environmental Protection Agency to meet that challenge. Researchers have developed software to support warning systems that provide real-time, reliable detection of contamination events, whether accidental or intentional. The tool is Canary, named for an early method of using birds to check air quality.
EPA shares information and provides technical assistance to thousands of water systems across the country, keeping them informed about threats to water systems and the latest detection, mitigation, and treatment technologies. Canary is being deployed at several of the largest water utilities in the nation through a series of EPA Water Security Initiative pilots. Water managers around the country are relying on Canary to help ensure the security of our water and also to improve water quality.
Currently, contamination detection happens through indirect methods, looking at individual sensors that show a change in chlorine levels, for instance. Canary uses specially designed algorithms to analyze the incoming data and differentiate between normal variability in water quality and unusual patterns or events.
You have water quality signals coming in from multiple physical locations, multiple different types of sensors at each location, and so that can very quickly become overwhelming. You have thousands of different data signals coming in.
It's typical to look at one sensor at a time to say pH cannot go above or below a certain level. And that would be what a utility would be primarily concerned about, so that they can deliver quality water to their customers. But we're trying to look for something a little more subtle, maybe a change that occurs across multiple sensors.
What we do is basically a filtering process. So we take maybe the most recent day or 2 days of water quality data, use that information to estimate what the next water quality value will be, whether it be chlorine or pH or conductivity, something else. We wait for that next observation to come in and we compare our prediction against that observation. If that's significantly different, we consider that an outlier. Now, we typically don't sound the alarm with one outlier, but we aggregate information over multiple consecutive time steps to build up evidence that the water quality has undergone a significant change. If a change has occurred, then Canary will sound the alarm.
I think that dealing with the variability in the data, especially to reduce false positives caused by normal operational changes, has definitely been the biggest challenge. Part of what I've done is helped find ways to make it so that it's more logical. You can more easily edit things and assign different parameters to a monitoring station and location so that it's easier to take, okay, these are the signals that belong here. These are all the ones I have to think about right now, and then we'll move somewhere else.
In this example, you can look at conductivity, pH, and chlorine and plot that in a three-dimensional plot and see how that data groups. And one of our algorithms takes these groupings and clusters them and keeps that in memory, so that when you come up to your next water quality data point, you can determine if that is normal or anomalous based on its multivariate distance to a cluster, to something that's already been determined to be normal. So these algorithms use some threshold that would point to a normal or anomalous water quality. The algorithm is fine-tuned to set that threshold so that you're decreasing the false alarm rate and increasing the probability of detection.
Canary is currently being used by several large utilities in the U.S., and with a multi-year project involving 70 monitoring stations, it's been very successful for the country of Singapore. Sandia's team offers substantial support for the free software, including hands-on training workshops, bi-monthly webinars, and a comprehensive website, and users are reporting additional benefits from these tools.
The utilities think about security, but it is not a day-to-day concern. It's something they think about occasionally. They're much more concerned with managing their system better, delivering high-quality water to their customers continuously. And what we found from the utilities that we have worked with is that a better managed system is also a more secure system, and vice versa. More secure is a better managed system. So they're really kind of finding now the dual use capabilities of Canary for better management of water quality within their systems.
Although the focus has been on water quality sensors, other event detection applications are being pursued, including in the world of cybersecurity. The team sees great potential for these tools.
This is open source software that meets a critical national need for security of systems that have not been considered or not been designed to be robust in the past. There is no way we can redesign those systems. The cost and expense are too heavy, so we really have to rely on enhanced monitoring of those systems to know if anything's going wrong. And that's exactly where Canary fits in.